connection. The title is written here. I would like to speak about connections between neutrino physics and grain unified theories. Okay, so just a brief reminder about yesterday. So we started yesterday with the standard model, that everybody knows, which has no neutrino masses built in. So there's no field which allows us to construct a mass field for the neutrinos at a renormalizable level. But we noted that in the standard model, if you accept that it is an effective theory, valid up to some energy scale lambda, we can introduce the dimension 5 neutrino mass operator like this here. So there's two lepton doublets, two Higgs doublets, which are contracted, and these get the vacuum expectation value. Then you get mass terms for the neutrinos. That's an effective operator, which means it's valid, so this theory is valid up to the scale lambda, where you have to introduce new physics to generate this operator. So there are, in principle, many ways to generate it, at loop level, non-perturbative effects, whatsoever. But at tree level, there are only three possibilities. These are particularly simple, and we will also recover them in grain unified theories, at least partly. So first possibility is to introduce right-handed neutrinos. So the right-handed counterparts of the left chiral neutrinos, these are total singlets under standard model symmetries. If you exchange them in a diagram like this here, and if these particles are very heavy, you can integrate them out of the theory. So this shrinks together to an effective vertex, which is nothing but this vertex here of the effective dimension 5 neutrino mass operator. Okay, one possibility, type 1 CISO, singlet fermions. Second possibility, instead of singlet fermions, you can have sp2 left triplet fermions, which can do the same thing. Also, if you shrink this here together, dimension 5 operator. Only difference is that this here is not charged under the sp2, so it's a triplet, so it has different phenomenological consequences in the end. But also fermion exchange kind of in this way, type 3 CISO. Next possibility is qualitatively different, is that instead of a fermion, you can exchange a scalar field. So you contract here two fermion lines through a scalar field, which then couples to the two standard model Higgs fields. So if these get their MEFs, this means this field gets an induced MEF, which is small, suppressed, when the mass of this field here is very heavy. We call this a type 2 CISO mechanism. Again, it's suppressed, and this field here has a large mass. Okay? So you can also see this diagrammatically, because we did nothing else than realizing this operator. So if this field here is very heavy, you can integrate it out of the theory. This means you can shrink this Feynman diagram to an effective vertex here in the middle. So again, you recover this picture. The scale of the physics is related to the mass of this guy here. Okay, these are the three CISO mechanisms. There's one thing I just mentioned briefly that, okay, Dirac neutrinos are kind of a special case of the more general case of having Majorana neutrinos, in the sense that when there is no lepton number violating mass term, no ML or MR in your big mass matrix, then you can realize the Dirac neutrinos. That's the other case, which we can distinguish experimentally from this one here, because here you have lepton number violation, here you don't. This is the case that we have only Dirac neutrino masses. So no Majorana mass contribution. You have right chiral neutrinos, but they are not allowed to have a Majorana mass term. You can enforce this by requiring some lepton number symmetry. If this is exact, so it would be a global exact symmetry, which is, well, questionable also from some context. But on the other hand, you can do this. You can write down this theory. You need a very small Dekama coupling for 1 10 to minus 11, roughly. And it's also more than just adding this right-handed neutrino to the theory. You also have to demand, as I mentioned, that you have an exact lepton number symmetry. So you are adding this particle and you're requiring an extra symmetry. Okay, so these are basically the mechanisms that you have, which are kind of the simplest. Then you have the loop mechanisms and so on, as I also mentioned only very briefly. Okay, now turning to the main point here, to the neutrinos and grain unified theories. Okay, first, again, want to make some preliminaries, so to go with you through some of the problems, but before I do this, just a brief motivation. So if you're looking for, which is the goal of the understanding of physics, as I mentioned, some more fundamental theory, then one motivation comes from the fact that we would like to explain where all these different flavor of parameters coming from, different properties of the fermion masses, and so on. And so we have these different types of fermions in the Standard Model, different types like quarks, up quarks, down quarks, charged leptons, neutrinos, and we have the 3 generations. So towards a more fundamental theory, one can try to extend the symmetries of the Standard Model to some bigger symmetry, or maybe kind of bigger but simpler symmetry, to understand the properties of these particles. And you can extend this in 2 directions. So one possibility is to extend this along this direction here, which is the direction of plane unified theories. One also says vertically. So you have kind of symmetries which combine all the different particles in representations of the standard, kind of representation of this new plane unified symmetry. So this also implies, or this is connected to the quest for combining or unifying the interactions in the Standard Model into a unified gauge interaction at some very high scale. But basically it's this split both. It's unifying the forces of energy, but it's also unifying the different types of particles at high energies. So that's the idea of grand unified theories. And the other direction, which is also interesting, and I will talk about this a bit tomorrow, is to have some symmetries in the horizontal direction. So for instance, including the 3 different generations particles into triplet representation of some horizontal symmetry groups, some so-called family symmetry groups. So these are basically the 2 extensions when you want to look for more fundamental symmetries than a Standard Model symmetry group. Today what I mainly want to talk about is grand unified theory. Okay. The problem that one has to face when one goes to such high energies, the grand unified theories, as I'm going to come to in the next transparency, suggest high energy scales around 10 to the 16 gigaelectron volt. Very, very high energies, then you're facing typically the so-called hierarchy problem in the Standard Model. So the simplest way to understand that the hierarchy problem is to look at the correction of the scalar field here of the Standard Model Higgs mass, and you consider this theory with a cutoff lambda. And you can calculate that by some loops, for instance here with the top loop, you get corrections to this Higgs mass of the order of the cutoff square. Right? So, and what we know, that if this cutoff is 10 to the 60 gigaelectron volt squared, then we have to somehow cancel this contribution to the Higgs mass by some kind of very fine-tuned bare mass in order to keep the Higgs extremely light. So that's kind of a stability problem, because you not only have to do this here at this one loop, but you have 2 loops, 3 loops, 4 loops, 5 loops. So at every loop level you have to tune again your theory in order to maintain it stable. And that's not a very nice property of a theory if you always have to do this. So there are various solutions proposed, and one of them is supersymmetry. So what is supersymmetry doing? It's solving this problem by requiring asymmetry. So we're adding superpartners here. For each Standard Model field, there's a superpartner with the same quantum numbers, but a spin that differs by half a unit from the spin of the original particle. So for every fermion, we have a boson as a superpartner. For instance, here, then we have, instead of this fermion loop, we have a loop of the so-called stop of the scalar partner of the fermionic top quark of the Standard Model. And if you calculate this diagram, and it has basically the same properties, it has the same couplings and so on, then you find such a contribution to the Higgs mass. And if you look back, this is exactly cancelling the contribution from the top quark. So we have same degrees of freedom. We have here a complex scalar field, and this exactly matches the other contribution with a different sign. So it cancels it. So if supersymmetry was preserved, there would be no such dangerous correction to the Higgs mass. Okay, so of course we know that supersymmetry has to be broken, so this is not a perfect mechanism, but it makes the Standard Model much more stable if such a supersymmetry would be there. Of course, there are other possibilities. For instance, this is just a problem for scalar masses. The fermion mass of the Standard Model, they are protected by chiral symmetry, so they don't have this problem. So if you can imagine that at some scale, a bit higher than the Standard Model scale, you can find that the scalar field, like the Standard Model Higgs field, it's not a fundamental field, it's just a composite field made out of fermions. Then above this scale, the theory would also be free of this quadratic divergence problem. That's these kind of composite models that solve in this way. Another possibility would be that there is in fact no really large scale in the theory at all, like the large extra dimensions. There would be a third possibility to solve it. And there are also some additional proposals. But for what is important for this talk is that kind of supersymmetry can solve this problem in this way. Because there's another attractive feature of supersymmetry, and this comes from the fact that when you want to build a grand unified theory, you have to construct a situation that you can unify the gauge interactions of the standard model into a unified gauge interaction. And for being able to do this, what you need is that the strength of the gauge couplings has to be the same at this particular very high energy scale. So this means you can then identify the generators of the symmetries of the standard model with parts of the generators of your big grand unified theory group, and you can really unify, or you have the possibility to unify standard model interactions. Okay, so what you have to do is you take your gauge couplings at low energies. They're like in every quantum field theory. These couplings, or the values of these couplings, depend on the energy scale that you kind of consider them. So you have to calculate the running of these couplings in your theory, and then you have to check if they meet at some scales. This here is the beta function, and one loop is just these two theoretical coefficients that you calculate from the standard model representations. Or if you go to the supersymmetric version of the standard model, the minimal supersymmetric extension of the standard model, the MSSM, then you get these coefficients here in your beta function. Okay, then you calculate the running, and you find that the MSSM, they indeed meet when kind of supersymmetry is here somewhere at low energies, then they indeed meet at a scale of 10 to the 16 gigaelectron volt, whereas in the standard model, they are, well, kind of running in the right direction towards each other, but they are not really meeting without doing anything else. But in the MSSM, they're kind of automatically meeting, giving you the possibility to unify these forces without much extra work at a scale of around 10 to 16 gigaelectron volt. So supersymmetry and GUTS fit together quite nicely. You have a solution to the gauge hierarchy problem. You have a meeting of the gauge coupling at a quite high scale, and you're kind of able to consider a stable theory up to these energies. Yeah, a bit more, what is supersymmetry? So we are not going to use any supersymmetric notation from now on, but I just wanted to mention a few facts. And then for the rest of my lectures, I will again return to some standard model notation again. But just to give you a brief idea what it is. So supersymmetry is, as already mentioned, the symmetry which connects particles with their superpartners with a spin that differs half a unit. But what it mainly is, it's an extension of the Poincaré's symmetry by fermionic operators, which generate supersymmetric transformations. So these here are the fermionic generators, and the commutator here, for instance, has a translation. Okay, now what this means is that you extend space to kind of a superspace. So in order to have the four-dimensional coordinate Minkowski space, you also have some coordinates of superspace, and also your fields will be promoted to so-called superfields, which means they have the, for instance, a Klein superfield as here the scalar field as its first component, and then here there's just a minus spinor degree field, so a two-component spinor. That's kind of a projected four-component Dirac spinor. Here, as this component, this is just an auxiliary field, which is something divisible, which you can eliminate by its equations of motion. The most important thing is you always have a scalar field here and a fermionic field together. Then these generators, they induce translations in superspace, and this means they can transform these two fields here into each other. This means in a supersymmetric theory, you can transform fermions into bosons. So they must have the same properties, the same quantum numbers, and so on. Okay, then you're normally giving the theory with a superpotential and also a kind of Kähler potential, which contains the terms. But from the superpotential, you calculate simply your Lagrangian for the scalar field and for the fermions, just with this formula here. So you just must have to take derivatives here. Set this value theta equals 0, then you have the fermion terms, or just the derivative here, modulus squared of superpotential gives you the scalar potential. And from this here, so if you see any supersymmetric theory, don't be afraid, just use this formula, calculate your Lagrangian, and you can continue as usual with your normal field theory, right? And from now on, I will also just continue discussing the theory as it was a normal field theory, but I don't think more, mainly of it as being a supersymmetry. Okay, so that's already enough about supersymmetry. I cannot do a supersymmetric course here, but I think it's quite interesting combination, great unified theory with supersymmetry. Okay, just last comments. We of course know that supersymmetry has to be broken, so we haven't seen the superpartners yet. They should be somewhat heavier than the electron weak scale, which is a drawback because this mechanism is not really perfect. Yeah. So some kind of tuning remains, but nevertheless it makes this theory much more stable than the standard model by itself. But this must be done in a way that we don't reintroduce quadratic divergences in that way. So we probably have a soft supersymmetry equation. This you can do by adding masses for this scalar partners, for instance. And supersymmetry also comes with these masses here and kind of other soft symmetry breaking terms like trilinear terms, comes with its own flavor structure. And this flavor structure can lead to flavor changing neutral currents, for example. This is the so-called supersymmetric flavor problem, which on the other hand, if supersymmetry was very light, it would be a very severe problem. Now that we know that supersymmetry is eventually a bit heavier, it's not so close to electron weak scale, then this problem also is not so severe. But there's another flavor problem coming with supersymmetric theory as well, which I'm not going to touch in this talk. Okay, now coming to neutrino masses in extensions of the standard model towards a great unified theory. Okay, so this is now very important to understand the rest of this lecture. So the most simple extension of the standard model that you can do towards a left-right symmetric great unified theory is called the minimal left-right model. So what you have here is you have the SU3 color of the standard model, you have the SU2 left of the standard model, but then in addition, so you want to make everything left-right symmetric, you also have a SU2 right symmetry. So now instead of your weak hypercharging one, you have here an SU2 right cross a U1 symmetry, which I named here B minus L, so you will very soon see why, because the quantum number is here, just by a number or the negative of the lepton number. But you are left-right symmetric, so you don't not only have a left U1 SU2, sorry, a left SU2, you also have a right SU2. So now, when you have your theory with just a symmetry group, you have to think, okay, how are my standard model fields fitting into the representations of this group? And here it is very intuitive and very simple, because we already named the charge lepton up and down quarks. We had some right chiral components in the standard model. So it's just natural to fit them into this SU2 right doublets, right? Okay. And that's what you indeed have in the left-right model, and that's why it's also considered very aesthetic, because you're not treating your right chiral degrees of freedom in the same way as the left chiral degrees of freedom. You can put them into doublets. So we have here. Okay, first to start with, we have the usual doublets that we know. So the left chiral fields are still in the quark doublet and in the lepton doublet. So the quark doublet here is SU3 color. It is charged on the SU2 left. Here it remains a singlet. And here, this is why we call it the B minus L. There's 1/3 of barrier number. So 1/3 of B minus L. Here we have the left chiral leptons. They have no color. They are doublets on the SU2 left. Also here, they are kind of singlets under the SU2 right, and they have -1 to the negative of the lepton number. So this justifies kind of U1 calling this B minus L symmetry. Now you can put your right chiral up quark and down quark into this right quark doublet. Right? And this is new. It is now charged on the SU2 right, not under the SU2 left. And so we're taking here the charge conjugate, again, like we did in the standard model, so it is -1/3 of barrier number. And now comes something very interesting, because now for the leptons, we only have the right chiral electron, but we have a theory which has an SU2 right, so we must complete this here to a doublet. So we are forced to write down a right chiral counterpart here of our left chiral neutrino, which is in the doublet. So the theory predicts that there is a right chiral neutrino. So it predicts that there is this guy here, automatically. And this will continue in all the other extensions that I'm going to tell you, which are kind of left-right symmetric, like partition models or also SO10 guts. They're all predicting a right parallel neutrino, which is a complete singlet in this standard symmetry, as we're going to see. So this is the Fermion content of the minimal left-right model, which is the first step towards an SO10 grain unified theory, if you wish. And it's very easy to understand this level. Okay, so now looking at the Higgs sector, you have to also break the electroweak symmetry, and you can do this here by having a Higgs which is a bidoublet. So it's basically it's a doublet of the SU2 left and the SU2 right, and indeed this contains two doublets of the SU2 left. So if you look at the components, then there's a phi 1 and a phi 2, so this is becoming, after you break it, a true Higgs version of the standard model. So a slight extension of the standard model, which is another amplification here. And here are two components here which are neutral, so these two components here can get vacuum expectation value to break to the standard model, the minimum left right theory to the standard model. Okay, so instead of the usual doublet, we had here two doublets put into a bidoublet. Then we also want to break this minimal left-right model down to the standard model symmetry group. And we can do this either by having here a triplet representation, delta right here. So this can do the breaking. Or if you can have another doublet representation here, which is called chi r. And this can also do the breaking of the left-right symmetry group down to the standard model group if it gets a vacuum expectation value. And if you want to make also the spectrum left-right symmetric, you will not only have here some right delta, you will also have some kind of left delta, and here you have some chi left in addition to some chi right. And here is how you calculated the electric charge out of from this field representation, from the weak isospins, where you have a weak isospin for the SU2 left, and then you have a kind of right isospin P3R, and then you have here the quantum numbers from the B minus L. So this basically extends also the Higgs sector, because you have to break this larger symmetry group down to the standard model. And you have two ways here, keep in mind, with the deltas and with the chi's, with triplets and with doublets. So this here is the breaking chain. So these fields can break from the minimal left-right model to the standard model, and then this bidoublet can further break it down to the SU3 color times you want to add electromagnetism, so it can do electroweak symmetry breaking. So now what does this mean for neutrino masses? So we've already seen that we're, in any case, including in the spectrum here, these guys, the singlets, the right cover neutrinos. But when we first consider the case that we are breaking the theory via these delta fields, so we have a delta R and a delta L, and this delta L is an SU2 triplet scalar field. Then we also have, oh, sorry, I wanted to write it down. Then we also have this ingredient delta L here of the type 2 Caesar mechanism. Okay, so now let's stick with this possibility. So which terms can we write down in the minimal left-right model that can then give masses to the neutrinos? Okay, so we have this coupling here. When you look with the two SU2 left doublets for the leptons, and these here contain the standard model neutrinos. And these can couple to the delta left field to the triplet. So this here is again the contraction where you can contract two doublets here to a triplet, and then the triplet can couple to this triplet here. So this is the notation that I introduced last time. Okay, so when this field here gets its induced BEV, then you get directly mass terms for the neutrinos out of this coupling. So this here couples the two left cover of neutrinos here. It gives my Majorana mass term directly for the left cover neutrino, but the left this here. So this here is the type 2 mass term. It's coming basically from this diagram here. Then what you also have is the left-right symmetric one. So the analogous one with the index R replaced by L, and slightly different convention with conjugate here. But this can give the same thing, but for the right cover neutrino. So it gives a mass term of the order of the map of this delta R field times this recovery matrix. So you generate now dynamically mass terms for this right-handed neutrinos. So not as we did in last lecture, we just wrote down a mass term, right? We had the MR, which is just the mass term that we wrote directly in the Lagrangian. But now this is connected to the breaking of the minimal left right model to the standard model. So this here is exactly the scale where we had the step-in symmetry breaking. So this here is at this scale. When this breaking happens, minimal left right to standard model, then the right cover neutrinos get a mass of this scale. Then if this is pretty big, then you can explain the smallness of neutrinos by the seesaw suppression. So this here is the new physics scale here, which is suppressing this operator. And here you have the standard cover couplings. This is a Dirac mass term. So this means these two here together just gives you the standard type 1 seesaw mechanism. So masses for the right-handed neutrinos, so this time we generate dynamically, plus these Dirac couplings, these Yukawa couplings. So we have a type 1 contribution, but in addition we also have this term here, this gives you a type 2 contribution. So we have a type 1 plus 2 seesaw, if you wish. So in a minimal left right model, if you break the symmetry via a renormalizable term, this means via such a delta R field, and you have a delta L field, and you have a type 1 plus type 2 seesaw mechanism. So the combination of both. This is what you expect as one possibility, also more generally in left-right symmetric extensions, and also from ascertained gas. But there is also another possibility, which is why I mentioned at the beginning, so you can break it either via the deltas or via the chi fields. The chi fields are simply doublets, they are not triplets, they are only doublets. And if you want to write your stem now, this is the second possibility, you get a pure type 1 seesaw mechanism. So you don't have a triplet in your theory anymore, you cannot construct a type 2 mass contribution, so this here is not working. But you still have to give masses to the right cover neutrinos, and these masses indeed emerge from an effective operator here. An effective operator of this type. It's very similar to, if you remember, to the operator that we had here for the left cover neutrinos, but now it's the analogous term for the right cover neutrinos. The difference here is that this scale, so the depth of this field here, will be very large. It's of the breaking scale of the minimal left-right model down to the standard model, or it can be very large. And so you get here masses for the right cover neutrinos of the scale of the pi r squared over lambda, where now lambda is something different actually as it was here. It's now the scale where you have to embed your minimal left-right model in something even more complete. So this may be the Planck scale, for example, and some complete theory which also includes gravity. So for instance, if you just play around a bit with the numbers, if you include here the gradient unification scale, this lambda here is a Planck scale, then this mass here will be Planck scale, will be Planck scale squared divided by the Planck scale. It comes out to be about 10 to the 13 giga-electron volt. And this is also just right for the type 1 seesaw mechanism. So you have two possibilities in left-right symmetric extensions. Normally, either you have a combined type 1 plus 2 seesaw, both contributions here, so this one and this one, type 1 and type 2, but this here from the delta L, which is basically optional. But this here, you always have this because you have the right cover neutrinos in your spectrum, and they must get masses. The empty number is always broken when you break the minimal left-right model down to the standard model. Okay? So either this here combined, or you have a pure type 1 seesaw mechanism. But since the number is always broken, you don't get this here. You don't get pure Dirac neutrino masses when you are in the minimal left-right symmetric extension, or in some bigger symmetry group that's included. Okay, so any questions up to this point about this minimal left-right symmetric extension? Okay, I see none, so I'm going to continue, but you can also, of course, ask me later. But because this is the first step if you want to go towards SO10 unification. So the next step is kind of adding something, namely it's unifying quarter electrons. That's called a so-called Parquet-Solin unified model. It's not a grand unified theory yet, because in the Parquet-Solin model you don't have a simple group, which is basically unifying all the interactions.